Oh crap, I forgot to send you the ELC3 stuff. You still interested in that?
Yeah, totally.
We have a weekly meeting today, right? We have a meeting today.
Yeah.
Hey everyone, we have a homework 6, which is a teaching evaluation as what you guys have been doing for me. Thanks for that. So deadline is next Friday. I think you will be able to start doing that next Monday, I guess. Will be available online. And we'll cover something about the some miscellaneous stuff. For example, the quiz, the project, and we'll wrap up models for circuit design, digital design today. And you'll be able to do the homework assignment over here. And next week we'll do the memory circuit design, and then IC power, IC yield, and something about the project again. And we're done for the semester. And I let you know I have posted the sample and hold circuit to the website. You can directly use it. And you can see the structure. So if you are using the 50 nanometer technology, you probably don't know how to size or how to scale the transistors. So I think whatever has been used for this circuit and the op-amp probably can be referred. You can probably borrow some of the transistors over there directly used for your other structures like the DFF or something. Did you make your DFF flip-flop work?
Mm-hmm.
Close? Okay, great. Is that a rising edge triggered or falling edge triggered? Quick question here for you guys. Rising edge. Let's take a look at this. Why is rising edge? Because when clock is 0, or at the moment of the falling edge, it falls to 0. And at that moment, the 0 is going to kill these 2 NAND gates, right? And give you 2 1s here. And that's the memory it's going to hold. So this one, I'm going to look at the data for every single line for you today. But right now, let's look at this, the very core features of this D flip-flop. So this is a rising edge triggered, and also this is a synchronous DFF. The reason is compared to the one we learned in logic, which is rising edge is sometimes the rising edge is gonna load the data to the intermediate line, and then falling edge will send the data to the output. But this one, whenever the rising edge arrives at this pin, the data here will be directly sent to Q. So it's synchronous. It doesn't have to wait another half cycle or wait for the falling edge to send it to the Q. So let's take a look at this structure and why this works in that way. So when clock is 0, because the clock is compared to the data, it should be a relatively faster signal, right? It's clocking, always oscillating. So there will be a moment, or always be a moment, is low, right? After the low, there will be a rising edge. But before the rising edge, at some moment, there will be a low over there, and it's gonna set these 2 pins. Is that correct? So the voltage low of the clock is gonna set these 2 pins. So in that case, right before the rising edge, for example, it is over here, you got 2 1s. Because 2 zeros will kill these 2 NAND gates and give you 2 1s over here. So whenever it's rising, this becomes 1 at that moment. So 1 is not affecting the NAND gates, so you can ignore that clock signal. It's going to enable the NAND gates, because what other pins will dominate the results of the NAND gates, but not the clock. It's just 1, right? 1 is not affecting the NAND gate. But you got 1 here already stored in there from the previous moment. So if data is 0, let's see if Q is 0 or not. That's what we want to verify. Because if it's a D flip-flop, if this is a D flip-flop, then whatever data, because data is relatively slower signal, right? So you've got a clock here. It's a clock, right? This rising edge, for example, we are looking at this rising edge. So I should be able to sample this data and send it to Q. That's the purpose of D flip-flop, right? Okay. If I have a fast enough clock, you couldn't even see all these gaps. So the Q will be very close to the input. Why? Because it is able to sample every single moment. And it's synchronous, so it's going to send every single data to Q. So it's going to duplicate the input, pretty much. Okay, but if you have a slower clock, it looks different because it has a delay. It has to wait for another rising edge to sample it and send it to Q. Because whenever after the rising edge, it's going to hold the value. So let's see, if data is 0, what's here? What's the data here will be? If this is 0, what is it? 1. This is 1. Yep. So this is 1, right? And we are not setting or resetting because this is operating TIDFF. So these 2 pins has to be what? Set and reset. These 2 pins has to be. These 2 pins have to be. Have to be. You can see a bar on the top. So whenever it is a 0, it's going to activate the set. So you need a 1 to release these 2 pins, which means you are not setting and resetting because this is operating right now. You want to sample the data. So this is 1. Clock is 1. At this moment, it just shoots to the high, voltage high. This was 1, and it is still 1. Just right before the rising edge, it was 1. It is still 1. So what's this signal will be after this? After the sampling, will be 0. It's going to be flipped. Okay. Then what about here? If this is 0, this will be 1, right? 1. Set has to be 1. Is Q 0? Is Q 0? Data is 0. Are we getting 0 for Q? We haven't seen this one, right? Let's double check. This has to be 1. This has to be 1. So what about this? If this is 1, this is 1, this is 1, this is 1, this is 0. It's going to Q it. It's giving a 1 here, right? So it's not changing that data. So Q will be 0. Verified. They're selling this D flip-flop. It has to be 0, right? If it's not 0, we are making a mistake, not circuit. So when data is 0, it works. It's sampling 0 and sending 0 to Q. So what about when data is 1? What's going to happen? So the clock is sampling 1. So previously you got 1 here, right? Because it was voltage low. So the voltage low is going to kill these two NAND gates and give you two ones. And now it's trying to flip it or not, doesn't matter. Depends on what is the data, right? So this is 1. Next. This is 1, this is 1, 1 has to be 1 because we are not resetting the circuit. So this becomes 0. 0, 1, stable. 0 kills this NAND gate. No matter what are these two signals, it's going to be 1. And clock is 1 because at the rising edge, at that moment, it is 1. And reset, 1. And 1 here, 0 here, 1, 1. It's going to be flipped. So this 0 is going to kill this NAND gate and give you a 1 here. So that's why when data is 1, Q is 1. Right, it's verified. So this is going to work. If it's not working LT Spice, let me know. We don't have that much time left, and do not stop anywhere. Feel free to send your schematic to me. I'm going to debug the circuit for you and send it back to you. And yeah, that's for the default file. Okay. And for the quiz. You really don't have to draw the fox. In the final exam, you don't have to draw the fox, all right? Another thing you need to know, so P select is not the area of the P plus, but the P active is. So so the P select always shows up with the P act. So the P select is the outer layer, but the P act is something in the middle. The reason you need the P select is it's trying to make the doping area a little bit larger, so it's not only specifically doping to that area. So what's happening in the doping process is the fox will block these dopings. So here's P select. But you have fox. So the P act is the main area which is the designer want to dope the P plus to the N well. So the P act is the opening. So it's going to open a little window on fox and remove that fox. But you need a larger P select because if you only dope to this area, probably it's not that accurate. You are doping to this part, so this part will not be doped. So in the larger area, it's fine because the fox will block all these doping or dopants to be doped to the N-well, to the substrate. So when you are drawing this, you just ignore the P select, just draw the P act. So first you need a P sub, right? On the label P sub. And then there's no N-well, so you don't have to draw N-well. But you do have a P plus. Here's the insulation layer. And this is a poly, and keep in mind, poly is floating in the insulation layer, and you have two poly layers, and both of them are floating there. So do not draw it directly on the top of the P sub. And another insulation layer, which holds the metal one. So you need here is one via, another via. So metal one is pretty long in this case. It's from here to here. That's metal 1. And then you also have a via connecting the P plus to metal 1, which is this. Right? And that's it. And then just label it. This is poly 1, this is via, and this is metal 1. For this one, start with a substrate. And you need an N-well. And P-act, P-select, and you just want to look at the P-act. So the P-act is going to give you a P plus. And then do you have poly? There's no poly. So poly has nothing, but metal 1 layer has something. So metal 1, you got metal 1 from here. So this box is for metal 1. The same size as a P well, the same width as a P plus. Sorry. And vias 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to draw 9 vias. Ideally, it should be the same width, right? The last one, also P sub first. There's no diffusion layers, so that's an insulation layer, and that's metal 1, and that's metal 2. And there's no metal 1. Sorry, I should draw it smaller. Starting with metal 2, so you should have a metal 2 layer here, and 2 vias, 3 vias. You do have a metal 1, sorry, you do have a metal 1 here. And a metal 3, this. That's it. Any questions? Anything? No? So you have 2 poly layers in the middle, right? They are floating in the middle, not touching any of the 2 layers. The metal 1 layer on the P sub is not. It's just floating in the middle. 2 poly layers. Poly 1 is lower. Poly 2 is higher. And for the SAR ADC block, we are going to simulate it. How can I simulate it? That's my first question. I mean, this is what I drew a couple of weeks ago when we were introducing this circuit. How can I simulate this circuit? It's a sequential circuit. Remember the final result? The final result here is actually what? Let's look at the one of the table on the right side. So give the comp, the result, the MSB to be 1 first, and then you are shifting that one to the left, to the right side, right hand side. And every time you got the comp, you put it in the front, and then keep inserting all the comps after that one. That's so slow. It's here. See, here's a table. That's the result. That's all the comps, the output from the comparator. And you can see the result is actually all the outputs of the comps. Right, because every time you are shifting this, all the numbers to the right, and you keep inserting all the comps in there. So in that case, the way to verify this circuit is in LT-SPICE. I mean, you give a sequence of the comp, and you give a clock to it. But at the very beginning, you want to reset this guy first. So you are creating a 1 here. And after that, you release this reset pin and allow the clock to trigger all the values or shift all the values. So if I draw the sequence for you guys, how do you want to design this sequence when you are simulating this, and how to verify it? Reset. So remember reset for the D flip-flop we just introduced from TI. Is logic 1 or logic 0 is going to reset everything. Logic 0, because you have a bar on top. So logic 0 is going to cue this NAND gate and give you a 1 here, so 0 here. So it's going to reset the result, right? And now we want to reset this guy, because we need a 1 here first. Even though it's called reset, but actually it's being shorted to set. So whenever I'm resetting all these ones, it's giving zeros. But only this one is being set, because it's called reset, but it's shorted to set, right? So if I give reset a what, then I'm getting 1 0 0 0 0. So at the very beginning, I want to initiate all the operation. I need to give a what kind of value, high or low, in order to create 1 0 0 0, because I need that 1 0 0 to start with, right? Remember all the state diagrams, you need a 1 0 0 0 to start with. That's the first state. 0. If you give a 0 here, it's going to set this D flip-flop, so it's outputting a 1, but all the other ones are being reset, so they're all zeros. So you have a 1 here, because all the wires are being shorted to here. 1 here is going to set this signal, and it's going to give you a 1, which is exactly the output at that moment. So it's going to be 1 0 0 0 0, right? Which is perfect. So in that case, what I need for this guy is 0 at the very beginning, and then I want to release it forever. What about the comp? You cannot predict it. Depends on the data. It's comparing with all the feedback signal every time. So comp can be anything, but you just want to just provide a dummy signal here for now, probably. Whatever you want to give it to it, but just cannot be too fast or faster than the clock, right? For example, just give us this kind of signal, right? And then clock, you can create a pulse signal for clock, which is a lot faster than comp, because comp is contains the data for the final output. So when you are doing this, you just give a clock. Okay, got more after this. It's a rising edge trigger DIFF flop. So at the rising edge of the first one, what's going to happen? Nope, because it's being reset during this period. It's not doing anything until here. Even this rising edge is not doing anything. Just couldn't do anything. It's going to start operating from this rising edge. And it's going to sample what? It's going to sample 1 here, and then sample a 0 here, and sample another 0 here, and sample another 0 here, and sample another 1 here. 1, 1, 2, 3, 4, 5, 6. 8. So for example, let's just do 8. Let's just do 8. Because this is a transient analysis, so whenever you are looking at these 8 signals, these 8 data, and you want to take a look at the output, which is here, or the Qs, we are doing a simulation. So you are hoping for the Qs, you are getting all these values, right? You want the Qs, all these Qs will give you these values. The comp equals to 10001110, right? 8 bits. And just probe all these Qs, see if you are getting these data in this specific sequence. And if you are getting this data at these moments, and I think this circuit is working, right? That's how you verify it. Any questions? Have any of you simulated this block? Not yet. Kind of. Try this, and let me know how that works next. Probably on Monday next week. Do you have time in the weekends to do this? Okay. Let me know on Monday how this works, right? This page. So let's look at the frequency calculation for ring oscillators. See how we do that. Why it's oscillating, right? Probably we are doing the lab. It's like magic. Why it's oscillating? So the odd number of inverters forms a closed loop. It's called a ring oscillator. It cannot be an even number. And the frequency of the oscillation equals to the number of the inverters in the ring oscillator times TPHL plus TPLH for each inverter. That's for each inverter, okay, and times n, times the number of inverters in the ring oscillator. And why is that? Intuitively, let's look at this circuit. I got 5 inverters. Cannot be 6, right? Has to be an odd number. think about that. Since every inverter is going to introduce a time delay, right? So for example, there's a rising edge happening. As long as it's not being held at 2.5 volts, so you know if the switching point is 2.5 volts exactly, then the inverter is not going to do anything, right? But anything even a little bit above 2.5 or a little bit below 2.5 is going to trigger the oscillator if the switching point is 2.5. So this is not stable. It's oscillating because you cannot guarantee this is 2.5. If it's even a little bit lower than 2.5, it's a positive feedback. It's going to drag all these voltages to either low or high. It's doing this. So for example, at this point, it's rising. Whenever this is trying to jump to the VDD. So what's going to happen for all these inverters? Whenever this is happening, it's a combinational logic, so it's not being clocked. It's going to be transmitted to all these following stages. So what's going to happen here is it takes time for this pin to fall, and then takes time to this pin to rise. It also takes time to this pin to fall, and takes time for this pin to rise, and takes time for this pin to fall. So it takes so much time to drag it down to the ground. So it takes time to go to the ground. That's the time it takes for the signal traveling from here to here. It's the same pin going back to this input. So that's why when it's rising, it takes some time to be put down to the ground. That's why you see a pulse. Is that making sense? Then whenever it is going down, whenever this is going down, it's doing the same job. It takes time for the pin to go back high again. And that's why it's oscillating. So how do we analyze the frequency? Because this oscillating has a specific frequency or period. How can we find out that period? So keep this in mind. So whenever, we're still looking at this period. Okay. So for this period, that's a half of the period, and that equals to what? Right? Whenever this is rising, this is falling, it takes time to fall. So it's going to be T, P, HL is falling, H2L, 1. And for the second one, it's rising, TP, LH, 2, TP, HL, 3, TP, LH, 4, and that time, that propagation delay for each gate, falling, rising, falling, rising, falling, forms this time period over here. And the same story for this part. Okay, so these two T's as half T, half T. And if you add them together, which is T, and these ones will be what? You add these two together. So these are how many HLs you have? 1, 2, 3, 4, 5. assuming all these inverters are equivalent. So they're all TPHLs. How many LHs? TPLHs. 5. Five is N. So that's why F equals to 1 over T, which is 1 over 5 TPHL plus TPLH. That's how you calculate the oscillating frequency of the ring oscillator. So see here's the equation, and all these that's a parameter, that's the number of the inverters you want to plug into this equation to calculate for F. Is that making sense? Okay. So how to calculate for these time delays? So if I ask you to draw the resistive and capacitive model, digital model of an inverter in the final exam, can you do that? How can I draw the digital model for this guy? Yep. So for input first, right? Input comes in, caps, and then disconnect everything because that's a gate, which is a dielectric material. There's no connection. That's RP, that's RN, and another 2 caps. And you need to know what are the values of the caps. Here's output, here's input. So what are the values of the caps? What is this one? Remember, you got here, 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 here. But for output can only see these 2. So every single one, physically, they are a half Cox P or Cox N. But for the ones that are being tied to the drain and gate, it has a Miller effect, so it becomes Cox instead of Cox 1. So for the input, when you are looking at the PMOS, you've got a half Cox here and 1 Cox here. So what's the total input for the P? 2/3. And same here. Cox N. What about this one? It only has the Miller capacitor for this cap as the output in terms of the PMOS, right? So this one will be Cox P and this will be Cox N. And if you connect all the inverters in a string, which is the ring oscillator, and the digital model has to be modified slightly because you are going to have another inverter behind it. So what's going to happen is, you don't have to look at this part, but let's draw it. What's being connected to the output? If you got an inverter following another inverter, so the output here should be shorted to the input of the next stage, which is going to be something like this, right? So you're getting another cap because everything behind it is being disconnected from the gate, so you don't have to draw it. So when you are analyzing the time delay as this output pin, you have to consider these 4 caps and these 2 resistors. That's all the components are going to affect the time delay, R and C's. Is that making sense? Great. So let's calculate it. I'm going to give you some examples regarding this. So for the output, what's the C total? C total. What is C total here for the output? So when you are doing AC analysis, or just looking at the rising edge, falling edge, charging and discharging the caps, you can imagine all these DC sources are AC grounds. It's confusing people all the time. It's going to confuse everyone for many years. But now let's just remember it. Okay, DC voltages are AC grounds. So when you are looking at these two ones, you want to flip it and short it to the ground. So actually have 4 caps in parallel, right? So what's C total? In parallel capacitors, you just need to add them together because it's adding areas to the plates. Wait, is it 4? So what is this one? Cox P, right? What is this one? Cox N. That's the output for the previous stage. So this one is the input, so it's going to be 2/3 of Cox P, Cox N. So C total will be 2/5, right? Oh, 2. I think you're right, but I think I made a mistake on my calculation. Let's add it together. So you have to add all these things together. Cox P plus Cox N plus 2/3 of Cox P plus Cox N, which will be 2/5, right?
5 halves.
Oh, 5 halves, yes. Mm-hmm. All right. So TPHL plus TPLH equals to 0.7. So for TPHL, for this node, HL means what? High to low. So when the output is going from high to low, which resistor is acting there? Is involved? High to low, Rn, right? So whenever it's low to high, Rp is involved. So if you add them together, you can factor 0.7 out and add Rn to Rp and times C total. Right? So that's how I calculate the variables in here for the frequency. So if you know this, definitely you can plug into here and find out the frequency of the ring oscillator. The ring oscillator can be used to provide really fast clock signal in digital circuits. Super fast, especially for what I have seen in my graduate school is on the publication, they use, because you can imagine, right? So this can be tiny, especially for the small technologies. So this can be tiny, and the frequency can be in gigahertz, multi-gigahertz. So it can be used for provide a shutter signal for high-speed cameras in a defense applications. Whenever they are trying to diagnose what's happening when there's an explosion happening, they need a high-speed camera. So that speed is not comparable to any of the high-speed camera available on the market. It's way higher, and they don't need the image. They just need a shutter, trigger the signal. Probably there's only a couple of photodiodes or a very small imager array, and they just trigger it, take an image, and then store it. They're not expecting to see any images, just see some of the spots. So this can provide super fast clock signal for the high-speed camera. And let's see example. Let's calculate it. Estimate So calculate the C total first. C total is 5/2 of cox n plus cox p, which is this. And that's going to be 4.7 Fametal. TPLH plus TPHL is 0.7 times 4.7 Fametal. They're getting up somewhere around 22 picoseconds. So you can see this is using the 50 nanometer technology from the model in the textbook. You can see the period. That's a super fast clock. So what is the frequency? FOSC equals to 1 over n (11 times). So if you have more stages, you get a slower or faster signal. At more stages, you have a faster or slower signal. Slower. So sometimes you want to slow it down. So just add more stages. It's just too fast. 4.16 giga pulses per second. Another thing you need to know, which is dynamic power dissipation. Because it's oscillating so fast, it's going to cause power issues. So if here is an inverter is driving a cap, what's the power consumption for this digital system? I know it's just an inverter, it's not a digital system, but all the gates are pretty much doing the same, it's just oscillating. So the way to calculate the power consumption, the dynamic power dissipation, is starting with the I average, is changing all the times, charging and discharging the cap all the time. You just have to find out average current. So the average current equals to Q total. Just find out the overall charges are involved in the charge and discharging operations. Q over what? T. That's the definition for I, right? What is Q? Q is a queen, right? It's a Victor and Charlie over T. So power average equals to VDD times I, which will be VDD squared times C total over T, which is also VDD squared times C total times F clock. So the conclusion here is the power consumption or power dissipation is a function of what? Clock frequency and what? Power supply and what? Load capacitance. Yes, 5 nanometer technology can run faster. That's why people are trying to fabricate their chips under 5 nanometer technology. That's what Samsung just screwed up Qualcomm's chip. It's just the power dissipation is getting higher. It's hard to control that. So that is going to take another year for Qualcomm to fabricate again with TSMC. And also power supply. If you don't have to use 5 volts, just use 1 volt. That's what the 15 nanometer technology you guys are using for your project is 1 volt, right? It's lower power consumption. And load capacitance, when you have smaller devices, definitely all these CGDs and CGS will be definitely smaller, but it cannot control the load, right? The load is the load, right? The customer is going to use that load for the circuit. So keep in mind, all these ones are going to affect the power dissipation for the digital system. Okay? Power consumption. So whenever it's charging and discharging, there will be power involved. And whenever it's running faster, you got more power involved, right? It's consuming more current power. All right, see you next Monday. Hopefully you get a chance to work on the SAR 80 SAR block in the weekend.